Okay. Good morning, everyone. My name is Sijie. I'm your host today in this episode of student lecture series, and the episode is 21. And I'm very delighted to invite and welcome one of my very good friends. Her name is Sijie, if I am pronouncing it correctly. And today her topic will be practical online fault detection with RF sensing. And before we start the presentation, let me quickly give a very short introduction, of our friend. Sijie is a final year PhD student in NTU. I was asking her about how the thesis writing is going on. Her research interests lie in wireless sensing, deep learning, smart health, and edge computing. Her research mainly works towards practical industry solutions and applications, and has published multiple papers in highly visible avenue. And I guess this is one from the Census conference recently she has attended. And I also like all the participants to mute themselves. And after the presentation, we can receive some of the queries. And yeah, till then, let me hand over this stage to my friend Sijie. Sijie, now you can start your presentation. You can share your slide and then start the presentation. Thank you so much.
Okay. So let me try. Am I visible?
Yes. Please go ahead.
And okay, let's get started. So thank you for the introduction and thank you for having me. Very good morning, everyone. My name is Sijie and I'm a final year PhD student. I'm happy to share my work, practical online fault detection with RF sensing, which actually is a real-time fault detection system based on Wi-Fi signal. And this work has been published in this year's census. All right, so as we are from various backgrounds, to begin with, let me touch on the keyword sensing. So you may wondering what is sensing, right? Sensing is to feel or experience something without being able to explain exactly how. This is the definition from the dictionary. For me, I defined sensing as an ability. For example, as a human, we could sense your boyfriend or your girlfriend or boyfriend and the girlfriend are unhappy. And we could smell something out of date, right? This is the ability to sense. So when it comes to science, we are trying to use different medium or modality to make it have the ability to sense, so-called XX sensing. Like, for example, we can use camera to sense, we can use acoustic to sense, and in this work, we use radio frequency to sense, which is actually the Wi-Fi signal, to be simplified. So how to use radio frequency to sense? Let's just take a Wi-Fi as an example to have a high-level idea of RF sensing. So Wi-Fi sending the signal from TX to RX. During the transmission, the signal will go through some, say, reflection, scattering, or reflecting caused by ambient objects and humans. This part of information actually be encoded in the Wi-Fi channel state information. So by decoding the channel state information, which in short is CSI, we can sense the human activities or surrounding objects. So in this work, we use the CSI to detect human fault. So, but then, why we use radio frequency to detect fault? As I just say, we can use like acoustic to sense, we can use like camera to sense, right? So as we all know, fault is a very important global public health issue. So definitely the research community had come up with many solutions to detect fault timely. However, acoustic-based solutions actually limited by the ambient loudness, and the sensing range is within 4.5 meters. And the vision-based actually is a camera-based sensing. It's limited by the line conditions. And most importantly, it will leakage the user privacy. As for the wearable-based sensing, wearable-based fall detection, like you use your Apple Watch to detect human fall. This one actually no user-friendly, especially for the adults, because they need to carry the devices, and also the devices need to be charged from time to time. So the RF sensing, which don't have the above limitation, and it's more suitable and promising in terms of fall detection. That's why we use RF to sense human fall detection, right? So existing RF-based solutions, they already have many solutions, but all existing solutions in general can summarize in these slides, which follow this pipeline. First, they will build up a data set with 4 samples, where the predefined 4 activities are performed within a fixed time duration, with the underlying assumption that only one activity happens during that duration. After that, they will use machine learning or say model-based to learn or to summarize a template to represent the fall. So during the usage, they detect fall by conducting template matching. So if the captured ongoing fall is able to match the template well, then it will report fall. But however, today I want to ask everyone a simple yet important questions. So what is fall? How to define a human fall? So let's just think about it for 1 second. I believe that you got the answer in the first second, but soon you will doubt yourself, right? Because you may don't know how to answer. This is because actually there is no uniform quantitative definition of fall thus far. So fall is diversity, which may be caused by external factors or internal factors. It's ambiguous, like lying and sitting. Actually, in a sense, they may look as fall as well, right? So what makes fall become a fall? So our answer is it's because fall is an accident. It's unforeseeable and it's uncontrollable. Then how can we learn a universal fall template to represent fall? Can we list all possible fall to collect data, or does a fall repeatable? With that is to say, existing RF-based solutions are deemed to fail in the real-life adoption, right? Because they all playing with the template matching things, but as you see here, actually we can't do the template matching. So our insight is that the fall is hard to learn, but if we think the other way around, the daily activities are learnable. It's consistent, and it's repeatable, and it's controllable. So why not we just learn from the daily activities and differentiate uncontrolled falls from recognizing repeatable and controlled daily activities? I mean, the idea is pretty straightforward, right? I know. But however, the daily activities are innumerable. What should we learn? And we even have some so-called real types of daily movements or some personalized daily movements. In that case, how do we learn, right? So to answer the questions, we propose a system called C4, and here is the overview of the system. About what to learn, the short answer is we learn from fall-like activities. The front end utilize channel dynamic to do a fault-like activity segmentation, so that the typical daily human movements without high frequency components are expected to be filtered out to narrow down to the learning space of the big A neural network model. About how to learn, we use the self-supervised fortnight with auto-encoder architecture to learn continuously and adaptively in the back end. So let's talk about the front end first. We utilize relatively clean CSI amplitude and mitigate the impact of noise CSI phase by calculating the conjugate multiplication of CSI for each subcarrier. So here a small background is that just now I'm saying that the channel state information actually can encode some human movement information in it, but the signal itself actually is very noisy, especially as we all know, the signal contains two parts. One part is the amplitude, one part is the phase. And in our case, the phase is very noisy. They have some a lot of combination of error. If I list it down, it will be M01, M02, M03, M04, etc. And the details actually in my paper. So here just a little bit background. We avoid the noise phase by calculating the conjugate multiplication. Then after that, the conjugate result only subjects to a random scaling factor M01 here, which actually introduced by AGC, the automatic gain control. The impact is time varying, so the CSI amplitude of a single subcarrier is time varying, even when the environment is static. But for each packet, the AGC impact across the subcarrier are the same. So the shape of CSI curve in frequency domain here are maintained, while when moving, the shape of the curve are changing significantly. So by computing the cosine similarity across time, we can get the channel dynamics that are caused by human movement. After that, we adopt a heuristic segmentation algorithm that incorporates with change point detection to segment the signal clip that have high frequency components with a pulse sign and consider it as a fault-like activity, and using the STFT spectrum as the neural network input. Right, like after fault-like activity segmentation, the different spatial streams STFT result will stack together along the channel dimension and form as a tensor to fit to the fault net. So the channel dimension here actually from different spatial streams, like for example, antenna 1, receiver antenna 2, and receiver antenna 3, like that. So then the fault net is an auto-encoder architecture, which only fill in the normal daily activities. And the goal of the network is to reconstruct the activity tensors as accurate as possible. The ground truth is the input itself. So here, we don't require any kind of data annotation. And the encoder runs a nonlinear transformation that maps the original data space with variable dimensions to a compact latent feature space with uniform dimensions, and then the latent representative Z. And then the decoder actually have the symmetric architecture of the encoder. It will learn to reconstruct the input tensor based on the latent representative Z. So for those 4 examples, because a network never learned it before, so FONET isn't able to reconstruct it well, which cause it will report error that orders of magnitude higher than those of daily activities. But then, although we use like just now we are saying we use some signal processing technique to narrow down the learning space to for-like activities, but which actually in a sense still innumerable, and besides some types of activities may be relative dominant owing to specific user activity patterns. So as a result, phoneme may be prompt to be overfitted. So to make the phoneme coverage faster and resistant to such overfitting and be generalized to functioning properly, instead of using a vector Z with n dimension to represent the learned for-like activities features, we adopt a bottleneck layer here with a stochastic sampling operation to make the phoneme become probabilistic. So in particular, we assume that each of the features of the IF signal follow a normal distribution due to the different body shape or different body orientation. So instead of learning a feature vector Z and reconstruct it from Z, we learn a vector mu and sigma to parameterize a normal distribution of the activities group. And then we random sample a vector Z from that distribution. If the network understands this group type of activities well, then it should be well reconstructed. Ideally, all normal samples from different daily activities together will form a mixture distribution of Gaussian. So compared with previous autoencoder structure, now the latent feature space is smooth rather than discrete. As for why we assume each type of daily activities can be represented by normal distribution, it's partly based on our observation from the experiment result. Here, the left part is from the same person, and for the right part, each row is the activity pattern of one person. We can see clearly that for those daily activities, no matter it's performed by the same person or different person, because of its kinematic consistency is similar, but because of the different body shape and orientation, it's similar but not identical, right? So in contrast, if we look at the 4 here and here, even for those performance by the same person, like this current, right? It is still very different. So we import this prior knowledge as a bottleneck layer to constrain the phoneme. So can make it the network more generable by adding this by adding the extra stochastic sampling. Then you may wonder how the network be safe learn. Just now we mentioned that the network will only learn from normal activities by reconstructing the signal clips, right? So here, we assume it has already learned a while. So we have calculated historical average error alpha, serve as a threshold when a new sample comes. If the error is less than the alpha threshold, it means it confidently taillights its normal activities. The alpha will be updated, and the model will also be updated by learning this new sample. If the error is bigger than alpha but smaller than 2 alpha, the average alpha will be updated, but the model will not learn from the sample. Instead, the sample will save to as a reference. After a number of reference samples is huge enough, say here we have 50 reference samples. The system will perform clustering algorithm for these reference samples, and we will feed the centroid of the biggest cluster to feed into the network to update. As it's a centroid of biggest clustered, as it indicate that this movement has been repeated a lot, right? So it which couldn't be in full, because just now I are saying a human voice hardly is impossible to be repeatable, right? Then after that, these reference samples will be discarded, except for those samples belongs to the cluster that is far away from other cluster, which we will consider it as a personalized movement. We will keep for further investigation. So such procedure will be repeated once the amount of the reference samples hit a number. And lastly, if the error is bigger than 2 alpha, the system will report a fault, but at the same time, save the fault samples with a timestamp. This is for a human to further investigate. If human check it's a false alarm, then the sample will be fed to learn and update the fault night. However, it's worth noting that this verification can be done at any time, not necessarily right upon the fault alarm. Okay, so we implement our system on top of the commercial Wi-Fi. To evaluate the system, we recruit 60 volunteers with different age, height, and weights and gender. All these volunteers is 56. We first conduct an intensive end-to-end evaluation in our test bed. 12 subjects are coming in sequence, and each of them move freely in the test bed, and the phone line is continuously maintained and updated throughout the experiment. As we can see, the system is getting better along with the time. The true positive rate is reached to 100% within 4 hours, and the false positive rate is 1.8% after 19.3 hours. We also save the model checkpoints after a person 6, person 11, and person 17. No, person 50. Yeah, to sneak into the deep neural network black box. This is the visualization result of each checkpoint. So we can see that the reconstruct daily activities is becoming more and more clear, while the fall are the other way around. So the network indeed become more sensitive to fall activities along with the time. We also conduct a 3 days long real-life adoption test where a subject living and work normally in an apartment, and the system is migrate from our test bed directly. Here is a number of false positive and their according happening time. So after 3 days learn from the daily activities, we conduct 3 types of fall in this location that denoted as red cross. We also conduct a rolling from bed fall and the sleeping fall, which is the subject want to sit on the office chair, but he fall. So the result is, except for the rolling from the bed fall, all the falls are successfully being detected. And here is a small real-time demo. And here is a real-time terminal output. And this is a ground truth. All right. Okay. so this conclude my talk. Please feel free to throw any questions or discuss anything. Yeah, so thank you very much. And Manoj, back to you then.
Yeah, Sijie, thank you so much. What an excellent presentation. You are really, really a good presenter, Sijie, believe me. Because you started right from the very beginning by the definition of, fall, and then you went to the importance of detecting it, and then how you actually apply encoder, decoder, and then finally giving a wonderful results of your experiments or of your proposed work. That was really an excellent presentation. So for the participants audience, if there is any question, you can unmute yourself, and then you can directly ask a question to the presenter, Sijie, and then or you can even write your questions or your queries in the chat box, and then I can repeat the same question to Sijie. So, but before receiving any queries, let me quickly ask a few questions, Sijie. So, why you actually decided to use the concept of encoder and decoder in your design? What is the motivation behind using encoder decoder in your system design there?
Okay, so it's the most important part is the encoder and decoder architecture is working in a say unsupervised manner.
Sijie, can you go to the slide number 7? Maybe that will be more.
Yeah,
this one. Yes, please go ahead.
Here, right? So
Yeah.
the encoder take let me say the encoder take the STFT spectrum as an input and reconstruct as an output. And how the encoder decoder work is like you want to reconstruct the input as accurate as possible. So it means that here the encoder don't need any kind of data annotation. So this is a very important part for my application, because we are saying that we want to learn from the daily activities. But the daily activities is huge.
Right.
And the signal is very hard to it don't like a image. Sort of we can see, oh, this is a cat, this is a dog, if I have semantic. But for signal, it's just a wave. Various types, various wave. Then how it's very hard for us as a human to keep annotating the signal itself. It's very expensive in terms of library also, right?
Right.
So this one is get rid of the human effort to annotate the data.
Okay. So my next question is about the alpha value. Yeah. So I was thinking like, this one, alpha update. So the system will be keep on updating the value of alpha, right?
Yes.
But how does it know that, okay, I shall not, once you get the very accurate value of alpha, so how does it know that it doesn't have to change, or it keeps on changing? What is it? Like, is there a kind of threshold of the value, alpha value?
So the alpha actually one of so-called nice function of our system is like we can keep learning and keep updating. So the alpha value is served as a threshold, but it's as you mentioned, it's consistently updated.
Right.
Yeah. So I know your concern. You may say like, how can I ensure the threshold is robust?
Yeah.
Right?
Kind of. Yeah.
So our hypothesis is because we only fit in the daily activities in the beginning. So here the alpha, we actually have a pre-trained stage where we use a lot of daily activities samples to train the model first. So we calculate from those samples for a nice alpha to start our model. Then, so in the beginning, the alpha is already a nice start point. But I want to say, even if we don't have a nice start point, because the daily activities, the number of daily activities is huge. So it can be generate a lot of samples in a very short period.
Oh, okay.
Yeah.
Yeah. So, Sijie, do you think that, well, before I put this question, I have another question. For example, I have a feeling that the samples you are, or the data set that you are giving as an input here is kind of simulated one. Is it how different it will be with the real one? For example, real one you cannot generate. I mean, it should be instantaneously, right? For example, you are walking on the road and then you fell down, or I mean, will there be a difference in, like, the real one and then this kind of simulation one, the image that you show here, like, the guy was like falling intentionally and with the unintention falling?
Yes. Actually, this one is a very good questions, right? So, first, as you see from the demo, instead of we ask the subject standing here, then we say fall, then he fall. Actually, he already is more like a freely to fall. But you are right. Even for it, we cannot ensure that the fall is the same as the clinical fall, right? So yeah, that's actually the big issue in our field. But for me, I just trying my best to conduct the experiments as accurate, as close to the real life as possible. So before I start the experiment, right, I actually summarize a lot of clinical report and clinical research paper, and I summarize 4 as 3 types. These 3 types of fall are try to represent different scenarios for, like the work fall is a things like the aiders are rushing to answer the phone. And stop fall is like it's like a stroke hit you or a heart attack hit you. You actually still have awareness, but you have maybe a little bit
consciousness. Yeah.
And it's kind of, so I summarize 3 type of falls, and during our experiments, I mean the 12 people can sequentially, we actually conduct all the 3 types of fall, and to make it as so because of the fall is a risk, high risky human activities. So when we need to conduct a human subject experiment, we need to go for the IRB, ask for improvement. So that's why we have to set up this kind of metrics to follow subject safety. This is a sort of trade-off between the realistic and the experiment. I couldn't say it's a real fall in a sense, but I really like try our best to make it like more close to real life.
Close. Right. Absolutely. I agree. So my next question, following the same question is, so you mentioned that you had an experiment with almost 80 participants. 60 participants. So would that be enough for training, or if you think it is not enough, then why? And if it is enough, how did you make sure that it is, I mean, the the sample size is good enough for this training purpose?
Oh, actually, this is no training stage. This directly is a detection stage. And
Okay.
Yeah, and here it's because our purpose to evaluate our system. First, it can be sensitive enough to detect fault. We are trying to make the false negative as small as possible.
Okay. Okay.
Yeah, which means we are trying to detect 100% fault. And the second part of our system is we are trying to verify whether our system can really update itself, whether our system can really
Okay.
along with the time. So this subject is here to verify the two things.
Okay.
So if we're talking about if the person of number is enough or not, definitely the more is better. But
right.
Yeah, but we already
Absolutely.
the main key is we want to verify. We want to verify it.
How accurately it can detect the fault. Okay, I got your point. Yes.
Better. Yeah.
Yes, that's it. Thank you so much. I think all participants have enjoyed your presentation talk, and if there is any queries or questions, they can, I think, directly email you, because we are going to upload this video to our YouTube channel, and there I think we can share your email, or we all know your email address, because I think you have already served GSC, right? As a GSA as a president also. So we know you very well. Once again, on behalf of SCSE-GSC, I would like to thank you so much for giving some time for this presentation, accepting our invitations, and I really wish you, a good luck for the final thesis defense. And yeah, we'll be in touch. Definitely, we'll be in touch. Thank you so much. And to all the participants, thank you so much for attending this SLS Talk episode 21. We'll be soon with SLS Talk 22. Please keep on tuning our SLS series. Thank you so much. Sijie, thank you so much. Good day. Yeah.
You have a good.
Yeah, thank you.
Bye. Thank you everyone for coming.
Okay. Bye-bye.
Bye bye.